So, hello my dear, I welcome you again in this session of most challenging questions. So today we will start with that thermodynamics subject. So in this subject we will discuss some beautiful concept and also there is a very good question, I know that you must like the question, okay. So we are not wasting much more time, we just start the first question. See my dear, this is your today's first question. What is the first question? See. Please read this question. The first question I will take intuitionally true and false. Whether the statement true and false. So first we'll write the statement. What is the statement? So state whether true and false. What is the statement? Is that there are two statements. There are two statements. First statement is statement A is work from 1 to 2 is equal to integration P dV, and this is equal to 500 kilojoule. This is first. And of B, second statement is entropy generation due to external irreversibility is 2 kilojoule per Kelvin. So first you have to check whether, that means whether this statement, one second, whether this statement true or false, and whether this statement true or false. Please check it. See my dear, if you are the this year, that means if you are the if you want to prepare the GATE for 2024, that means upcoming, you must have to solve this problem. Why? Because I damn sure this type of question must be asked in the upcoming GATE. And my dear, if you are able to solve this question, it is damn sure that you have a concept in entropy balance. So this question we have to take intuitionally. What is the question? I will read this question first. Heat is transferred from a heat source at 1000 Kelvin to a simple compressible system with a system boundary temperature of 500 Kelvin. During the process, there is a total heat transfer of 1500 kilojoule to the system. During the process, entropy of the system increased by 5 kilojoule per Kelvin and internal energy increased by 100 kilojoule. This is 100 kilojoule. The system mass is 1 kg. State whether the statement, the given two statement is true or false. That means the first statement is work transfer, the work done is integration P dV is equal to 500 kilojoule. Option B, entropy generation, S generation due to external irreversibility is your 2 kilojoule per Kelvin. So these two statements, first identify these two statements true or false. Please tell me beta. Really this question is my favorite question and this question is very good question. Okay. Now, so what is given here? We'll start this problem. Okay. See my dear. This is very good question. I am telling you literally, I am telling you beta, this is very good question. Okay. Yes, start with that one. So let's suppose there is a system and system is a simple compressible substance. Okay. So this is our system. Let's suppose this is our system. Okay. Okay, this is our system. Let's suppose this is our piston cylinder. This is our piston cylinder. This is our piston cylinder. This is our, and this is our system. This is our system. This is our system. Let's suppose this is our system. Okay. This is our system. Okay, no problem at that. This system is a simple compressible system, and we have to transfer a heat. We have to transfer a heat from the surrounding. See, this question it is given, the heat is a transfer from a heat source. That means there is a source, and source temperature is 1000 Kelvin. So there is a source. So from here we have to transfer a heat. From here we have to transfer a heat from this source. Let's suppose this is our source. This is our source, and from this source we have to transfer a heat to the system. That means we have to transfer the heat to this system. We have to transfer the heat to this system. One second. We have to transfer the heat from this to this one. Okay, we have to transfer the heat. Now, my dear, in the question it says that, this is very good question, I am telling you. In this question they says that system boundary temperature. That means heat source. Okay, so heat source, that means a reservoir temperature, T of reservoir, yeah, T of surrounding. It is given how much? 1000 Kelvin. Clear? Okay, from 1000 Kelvin. And the system boundary to a simple compressible system. First, what is the simple compressible system, beta? The simple compressible system is a such kind of system which have a no effect of electrical, magnetic, surface tension. That means at the surface of the system which have a no effect. We cannot take a consideration of a electrical, magnetic or surface tension effect. Such type of a system is known as simple compressible system. Okay, no problem. With a system boundary temperature 500. That means this is your system boundary temperature. This system boundary temperature, T of boundary temperature, this is given 500 Kelvin. That's it. That's it. Okay. Now, then during the process there is a total heat transfer 1500 kilojoule. That means in this one the heat transfer Q1 to 2 is 1500 kilojoule. Okay, 1500 kilojoule. Clear? 1500 kilojoule. Okay. Now, my dear, done. Now, the next is during the process entropy of the system increase. That means system entropy is increased. That means what is the system entropy? Given. It is given system entropy, that means delta S of system, and it is a property, that means S2 minus S1, and these are positive. Why? Because it is increased. How much? 5 kilojoule per Kelvin. No problem at all. No problem at all. Now, second one, it says the second condition, internal energy increased by 100 kilojoule. That means internal energy, that means delta U of a system, that means U2 minus U1 is equal to your 100 kilojoule. This is given. This is given. Okay, no problem at all. Now, my dear, they are asking, so forget about all the things. First, find the work transfer. Why? Because the statement first is work transfer. So we'll check the work transfer. How to find the work transfer? So to find the work transfer, we have to apply the first law of a thermodynamics. So first law of a thermodynamics, first law of TD, What is that? What is that? Process 1 to 2 U2 minus U1 plus W 1 to 2. Okay, what is the heat transfer? This is, if this system heat is in positive, so 1500. U2 minus U1 it is given 100. 100 it is given? Yes. No, U2, this is 1000 beta. Increase by 1000. This is 1000, okay? So in this question, this is 1000 it is given. 1000. Don't bother about that. This is 1000. So 1000 plus W122. So W122 is equal to 500 kilojoule. Okay, we'll check the option. This is yes or no? Yes, 5 kilojoule. Correct. So what is your option? It is true or false? Please tell me, everyone. It is true or false? Please tell me, everyone. Please tell me, beta. This is true or false? This is true or false? Okay. You say that's yes, sir. This is true. No problem. Okay. That means this is true. This is true. Okay. Then we'll check the second one. Okay? Okay? This is true. Why? Because work 1 to 2 is 500 kilojoule. This is true. Clear? Now, take the next one. We have to find the S generation due to the external irreversibility. We have to check the S generation due to external irreversibility. See, my dear, who is the responsible to who's fellow responsible to external irreversibility? Please tell me. Who is the fellow responsible to external irreversibility? Please tell me. Who is the fellow responsible to external irreversibility? Will finite temperature difference. That means heat transfer. Heat transfer to a finite temperature difference that are responsible to the external irreversibility. So we'll check whether the value of external irreversibility is 2 kilojoule or not. Okay. So for that one, we have to apply the second law of thermodynamics. So second law of thermodynamics. Second law of TD. Entropy balance. Yes or not? Entropy balance. Okay. Now, my dear, this is closed system or open system? This is obviously closed system. Yes or not? We'll take the system is closed. We have to take also the system is open, and then you have to justify your answer. No problem. Simplicity. We have to take a closed system. So, what is the entropy balance of a closed system? Please tell me. S2 minus S1 is equal to Q122. Okay, we'll take like that, no problem. S2 minus S1 is equal to, okay, no problem, Q heat transfer 122 by temperature plus S entropy generation. No problem at all. No problem at all. Okay, this is the entropy balance for a closed system. Why? Because the transfer, this is the transfer mechanism, this is the change, this is the system, this is a transfer. Here transfer only by the heat, no mass. So this is the transfer, entropy transfer by the heat. This is the entropy generation. And this entropy generation, it is a path function. But this entropy change, it is a point function. So this is the system. And this is the generation. It depends upon the path. That means whether it is a reversible, the generation is 0, and whether it is irreversible, generation is positive. It is never negative. Now, this is due to the heat transfer. So, in this case, in this model of the question, only the transfer phenomena is heat. So, there is no any mass transfer. So, we have to assume the system is closed. Clear? Now, so this is okay. Now, my dear, we have to find. So, S2 minus S1 it is given, S2 minus S1 it is given, heat transfer it is given. What is this temperature? Please tell me. Please tell me what is that temperature? Everyone please tell me. What is this temperature, beta? Please tell me. What is this temperature? Whose fellow will decide what is this temperature? The fellow is generation. That means what type of generation you have to find. If you find the internal generation, that means generation due to internally, put system boundary temperature. I am telling you. If you find the total entropy generation, put surrounding temperature. This is very important, I am telling you. If you find entropy generation internally, see, if you find S generation internal, due to internal irreversibility, what is the S generation? So corresponding, the temperature is equal to temperature of system boundary. Clear? System boundary. If you find entropy generation total, S generation total, if you find S generation total, the temperature, it is your temperature of reservoir. Temperature of reservoir. That is the main thing is there. Okay. Now, and you know that entropy generation total is equal to S generation internally plus S generation externally. Clear? So from here you can easily find what is the S generation due to external. What is that? S generation total minus S generation internal. Okay? Okay? That is okay? Now, so entropy change it is given. How much entropy change it is given, beta? 5. Yes or not? See? 5. Heat transfer it is given. Why? Because this is our system, so heat added 1500 divided by, if you put this temperature, system boundary temperature, what is the system boundary temperature then? 500. If you put this 500, so here this S generation is internally. Clear? Here S generation is internally. So if you take this one, so how much this is? So internal heat generation, how much it is? It is your 2 kilojoule per Kelvin. This is your internal heat generation, internal entropy generation. Clear? Clear? Now, if you find external, so first find total. How to find total? Again, S2 minus S1 is 5. Heat transfer is 1500 divided by, in this case, what is the temperature of reservoir? 500, 1000. 1000 plus S generation, and that is your total. That is your total. Okay. So what is the S generation total? Total how much, beta? The total is, if you calculate this heat generation total is 3.5. Clear? So what is the external heat entropy generation due to external? Entropy generation total 3.5. Entropy generation internally 2. How much it is? 1.5. Clear or not? Clear or not? Clear? So, but in this question, entropy generation due to external irreversibility is your 2 kilojoule per Kelvin. Here, it is your 1.5. So the answer is false. Answer is false. Answer is false. Okay. The option, this option is false. This option is false. Clear? Happy? But Happy, but there is a mistake. What is the mistake here? There is a mistake. What is the mistake here? Yes, this statement is correct. That means this statement is false. Yes, why? Because S generation due to externally, here we have to see that X generation internally is 1.5. But now, my dear, see this very closely. Work transfer is equal to integration PDV is not valid. Why? Because in what condition work transfer is equal to integration PDV is valid? Please tell me. Under what condition integration PDV is valid? Please tell me, everyone. In what condition the work transfer of integration PDV is valid? Only the quasi-equilibrium process. Under what condition? Quasi-equilibrium process. And the quasi-equilibrium process is internally reversible. Quasi-equilibrium process is internally reversible. That means, but in this question, if you find there is a internally irreversible. See, there is a, why? Because there is a generation. That means this process is internally irreversible. If this is 0, if you calculate and this value 0, then in that case you have said that yes, the option is correct. But in this question, there is a internally irreversible process. Why? Because there is a must be a generation, that means greater than 0. That means in this question you have to know, you are not applying work transfer is equal to integration PDV. Yes, work transfer is equal to 500, correct. But in this question intentionally put work transfer is equal to integration PDV. That is wrong. That is wrong. Why? Because if you apply this one, only you have to apply due to internal reversible. Why? Because quasi-equilibrium process and internal reversible, then S generation internally is equal to 0. In that case you have to apply. But here it is not 0. So we cannot. So this statement is false. Correct? Correct? Correct na? Correct beta? Okay? Good. This statement is false. Now, I have to take the next problem. Next problem. What is the next problem? Please tell me. This is the next problem. Please read this question carefully. This is your next problem. Please read this question carefully. This is your next problem. Please read this question carefully. Consider steady heat transfer through a 5 meter, this is cross beta, 5 cross 6 mm bricks wall of a house of a thickness 30 centimeter on a day when the temperature of outdoor is 0 degrees centigrade. This is 0. This is 0 degrees centigrade. Outdoor is 0 degrees centigrade. The house is maintained 27 degrees centigrade. 27 degrees centigrade. The house is maintained. The temperature of inner and outer face of the bricks is measured. Inner 20 degrees centigrade and outer 5 degrees centigrade. Okay, respectively. And the rate of heat transfer through the wall is 1035 watt. Determine the rate of exergy destruction in the wall and the rate of total exergy destruction. That means wall and total exergy destruction associated with the heat transfer. So only there is a exergy transfer. Here the exergy will transfer only by the heat transfer. So my dear, what is the balance between the energy balance? There are three balance: energy balance, entropy balance, and exergy balance. In energy balance, energy transfer is associated with heat, mass, and work. Entropy balance, the entropy transfer is associated with only heat and mass. Again, exergy balance, that means the exergy transfer is responsible due to the heat, mass, and work. Due to work also the exergy will transfer. But due to the work, entropy will not transfer. So transfer of energy will be mass, heat, and work. Transfer of entropy only by heat and mass. Transfer of exergy is due to the heat, work, and mass. Only here this is the wall, and wall it is only transfer the heat. So we can take this wall as a closed system. That means we have to balance the exergy of a closed system. Okay. So this is your one phase. This is your one phase which maintain 20 degrees centigrade. So this is your inner, and this is your out. And this is your outer phase will maintain 5 degrees centigrade. And outside surrounding it is your 20 degrees centigrade, and inside surrounding it is your 27 degrees centigrade. And heat will transfer from high temperature to low temperature. Clear? So we'll try to solve this problem. Okay. So try to start this problem. This problem also is very good problem. Let's start with this one. Okay. Okay, my dear. So this is your wall. This is your wall. Yes or not? This is your wall. Okay. This is your wall. Correct? No problem at all. And in this one there is a heat transfer. There is a heat transfer. There is a heat transfer. Now my dear, this wall have a maintain this surface maintain this face and this face. There are two face. This is inner face, this is outer face. So inner face will maintain 20 degrees centigrade and outer face will maintain 5 degrees centigrade, so that heat will transfer. This is your heat transfer. Clear? Now inner face inside temperature 27 degrees, that is this is your surrounding temperature. Outer side of outside temperature 0 degrees centigrade, and this is your outer surrounding. This is your inner surrounding, this is your outer surrounding. So due to this heat transfer, what is the exergy distraction? What they are asking that? Exergy distraction. What is the exergy distraction? Exergy distraction, that means irreversibility. So what is the irreversibility associated with the wall? In the wall, and irreversibility, total irreversibility associated. Clear? So we will have to solve this problem by two methods. Hi beta. Hi, hello Vansal. Okay, JEE Telecom, SSC JEE CGL technician vacancy का. I don't know beta for the SSC. This is for the gate. If you prepare for the SSC, you are not here. Okay beta, this is exclusive for the gate. Okay, so I think you just waste your time. If you have a preparation for the gate, then it is helpful. Okay. No, beta. I am not. We are not just start with the SSC JEE. This is this coaching is only dedicated for the gate. Only dedicated for the gate. If in future, if we have any ideas about the SSC JEE, we'll inform you. No problem. Okay. Okay, beta. Thank you very much. So this is 20 degree. Now exergy balance. Now my dear, what is the heat transfer? This heat transfer, it is given how much? 1035 watt. Okay, clear? It's a technical paper, but the SSC JN beta, SSC JN na. So SSC JN are differ from the GATE. The syllabus is also differ. Yes, if you have a prepare for SSC JN, you can prepare for GATE. But the GATE is something will little bit differ. Yes, syllabus by same. See, all the syllabus are your BTech syllabus, but the standard are differ, approach are differ. While you preparing the SSC examination, technical examination, main paper examination, so in that one you have to prepare for the according to GATE. But GATE orientation, or for the GATE we are orientation for the numerical. But the SSC JN numerical plus theory portion both. You can prepare for that one. Approach are differ. These are the diploma basis and these are the BTech basis. Okay. But if you, yes, if you know about, if you have a very good knowledge about the technical paper, you can easily understand the questions or all these questions, no problem at all. Okay. I am not teaching here for the GATE and for the SSC JN, for ES, AS. I am just in front of you with that concept of thermodynamics. Yes. Wherever you have a thermodynamics, this concept is useful. That's it. That's it. Okay. Thank you. And the system. First, what is the system, beta? Here, what is the system? System is wall. Yes or no? System is what? Wall. Wall is our system. This is your wall. Wall is our system. Okay. This is your wall and wall is our system. And this system wall, only we have to transfer the heat. So this is your closed system. This is your closed system. Only transfer a heat, that is your closed system. Okay. So we have to exergy balance. See my dear, you can solve this problem also with the help of entropy generation. What is that? Exergy. Why? Because this is your watt basis, joule per second. So rate basis, exergy in minus rate of exergy out minus rate of exergy destroyed. This is your measured by the irreversibility is equal to dx of the system, exergy of the system by dt. Now my dear, this is the steady heat transfer. This is your steady heat transfer. So this is 0. Steady heat transfer. Steady state. Okay. Steady state, this is 0. So now this is your exergy transfer. This is your exergy transfer. That means this is your rate of exergy transfer. In this case, by heat. In this case, beta, in this question, only heat. This is your exergy, rate of exergy distraction. This is your rate of exergy distraction. Clear? Rate of exergy distraction. Now my dear, what is the exergy transfer due to the heat? Please tell me. What is the exergy transfer due to the heat? That means, see, if there is a system, I will tell you, if there is a system and if you transfer heat to the system Q and this system temperature is T and let's suppose surrounding temperature is T naught. So what is the exergy transfer? That means what is the availability? The exergy transfer for this one due to the heat is equal to this heat transfer into 1 minus surrounding temperature divided by system boundary temperature T. This is your exergy transfer by the heat. Exergy transfer by the heat. This is a formula. So exergy transfer by the heat. Now my dear, there is a destroyed, exergy destroyed. So for the wall, if you take exergy destroyed for the wall, that means what is our equation? The equation it is like that. See my dear, the equation it is like that. See, that means exergy change, rate of exergy change. So how we will write like that? One second. That means, see, exergy change x2 minus x1 is equal to, what is that? Exergy transfer by heat. Exergy transfer by heat. That means rate of exergy in minus rate of exergy out minus exergy destroyed. Rate of exergy destroyed. Now my dear, if we have, so this is 0, this is 0, no problem. Why? Because this is steady. So finally this is 0 for all the case. This is 0 for the steady. Now my dear, if we have to find exergy destroyed, so what is the here? What is the exergy in due to the heat? 1 minus surrounding temperature by T of in minus heat transfer 1 minus surrounding divided by T out minus x of destroyed. Yes or not? Now my dear, if we have find exergy destroyed, exergy destruction destroyed in the wall, that means for the system, exergy destroyed internally, wall, that means internally, exergy destroyed for wall, that means within the system due to the wall. So in this case, we have to put wall in temperature, wall outer temperature, Now if we have exergy destroyed total, so we have to put here, if you put here wall, this is total, right, total. So for the total exergy destroyed, we have to put here T of surrounding in and T of surrounding out. That's it. That will depends upon. So in this question, first it says that what is the exergy destroyed due to the wall? So we have to write like that, Q dot 1 minus T by, if wall, that means a wall temperature, या boundary temperature, you have to take a boundary temperature inside minus heat transfer 1 minus T naught by boundary temperature of outside is equal to exergy destroyed due to the wall. Now my dear, heat, what is the heat transfer here? The heat transfer, it is 1035. 1 minus, what is the temperature T naught? What is the temperature here T naught? Please comment beta. What is the temperature T naught? What is the temperature T naught here? Please comment. What is the temperature T naught here? T naught is the dead system temperature. That means this is the minimum temperature at which the temperature not decreasing. So after that, temperature is not decreasing. So in this whole system, what is the minimum temperature? 0 degree. That means this is a dead state system. Below that, the system will never reach That means this is your dead state system. So in the exergy, we have to dealing with the interaction also. So exergy, it is a property beta. It is a binary property which deals with the system as well as surrounding. What is the condition of surrounding? If you don't know what is the condition of the surrounding, you can never find the exergy or available energy or availability. So exergy is a binary property. Yes, entropy is a system property, energy is a system property, but exergy is a binary property which related with the system as well as surrounding. So that is the binary property. So what is the surrounding? Surrounding is we have to check the surrounding. What is the minimum? Minimum is 0 degree. That is a dead system. A dead system, a dead man never interact with the surrounding. Dead man is absolute. That means dead man. So at what level you have to take, you have to available the energy at what level, what potential of energy, what potential of work. The potential of work is maximum you have to take at a 0 degree. That means if the system will reach the 0 degree, the system will be a dead system. Okay, so we have to put here 20 degree, 0 degree. So 0 degree is what? 0 plus 273, and inner boundary temperature is 20 plus 273. 20 plus 273 minus this is 1035, 1 minus what is the outer 0 plus 273. What is the outer boundary temperature? Outer boundary temperature is 5 degree. So 5 plus 273. This is equal to exergy destroyed due to the wall. So please solve this one. If you solve, so the exergy destruction in the wall is equal to, if you find, this is your 52 watt. This is your 52 watt. Clear? This is your 52 watt. So this is a wall. Yeah, internally. You can say that internally. Now, the second question in this one says that what is the and the rate of total exergy destruction associated with the heat transfer total. So for the total, we have to take the surrounding temperature inner and outer. Okay, so we have to write for the total. So what is that? Exergy in. Okay, so we have to find the exergy destruction total. For the total, we have to take heat transfer 1 minus minimum temperature divided by, this is the temperature of the surrounding, inner surrounding. Inner surrounding, okay, minus, this is your minus heat transfer 1 minus T naught, and this is your temperature of outer surrounding. Clear? This is the exergy transfer. Okay, sir, please go through the Jharkhand SSC JTCCGL technical vacancy notification sometime in that paper 3, okay, 100 question belonging to technical question. Okay, okay. Okay, beta, I will think that, I will consider your comment, okay. Thank you, I will consider. So this is for the total. So put this value here again, 1305, 1035, 1 minus surrounding as it is 0 plus 273, inner surrounding it is your 27 plus 273 minus heat transfer 1 minus 0 plus 273, and outer surrounding is also 0 plus 273. Clear? So this is 0. So if you find this one, this is your 93.2 watt. Clear? Right? So this is your exergy destruction total, and that is for the wall. So my dear, this is your total exergy destruction, total. That means this is a total irreversibility, and this is your internal irreversibility. So if you differentiate this one, if you differentiate this one, there is a certain value. So that certain value is what indicates, please tell me, this is your total exergy destruction, and this is your wall exergy destruction. If you differentiate it, certain value you have. What the value, that value what indicates? Please think that one. Okay, please think that one. This is the exergy destruction due to the wall. This is the exergy destruction due to the total, that means responsible heat. If you differentiate that, there is also exergy destruction, and that exergy destruction, who is the responsible fellow? That is my question. Okay, please think that one. Okay. Now the next question is this one. Please read this question. This is very good question. This is very good question, important question. Please read this question, beta. Air enter a steady flow adiabatic turbine at 1600 Kelvin and exhaust to atmosphere at 1000 Kelvin. Atmospheric pressure is 1 bar. If the second law efficiency is 85%, first, what is the turbine inlet pressure? Second, what is the irreversibility during the expansion process? Why? Because we know that in the turbine there is an expansion process, and due to the expansion, there must be irreversibility. So you have to measure that irreversibility. Given that the surroundings temperature is 25 degrees centigrade and properties value it is given for the air, that means at 100 degree the enthalpy and entropy, 1600 enthalpy and entropy it is given. Clear? Clear? Everyone please tell me. This is clear. This is very good problem. Please tell me, beta, this is clear. Okay. This is very good problem. Okay. Clear? Now we have to take this one. Okay. Okay, beta. We'll start. Let's start this problem very quickly. Let's start this problem very quickly. Okay. So there is a turbine. This is your turbine. It is given. And precisely there is a gas, air. So this is your gas turbine, I think. This is your air. In this one, the air it is handled, turbine. This is your air. And this is turbine. Okay. Clear? Okay. This is your in section. This is your in section. This is your exit section. Okay. This is your in, and this is your exit, and this is our a control volume analysis. Yes or not? This is our control volume analysis, and this is our shaft. Clear? Clear? Now this, in this one it says that this is inlet, yani this is 1 and this is section 2. Okay. So here it is given T1. How much it is? 1600 Kelvin. And here P1 we have to find it. Okay. Now, second condition, T2 it is given how much expansion it is take place. Expansion, that means T2. T2 it is your 1000, expansion up to 1000 Kelvin, and pressure is equal to the surrounding pressure. P naught is equal to 1 bar. Surrounding 1 bar. Okay. And this is your atmospheric pressure. And the surrounding condition it is given. T naught it is given how much? It is 298. Clear? R, this is air, so R value it is given how much? 0.287 kilojoule per kg Kelvin. Okay, it is given. R value it is given. No problem at all. Now, the expansion will take place in the turbine. The expansion will take place adiabatic. Why? Because in this question says that steady flow adiabatic turbine. That means there is a no heat transfer. So what is that? Only mass transfer will take place. Mass transfer will take place. Mass transfer. Okay. Mass transfer will take place. There is a mass transfer. Mass in and there is a mass out. Clear? Mass transfer. Now, so expansion is adiabatic in the turbine. Expansion is adiabatic in the turbine. Expansion is adiabatic. Correct? Now, what is the second law of efficiency, beta? What is the second law of efficiency? You know that? That is your useful work output. Work output divided by maximum possible when there is a maximum possible output work, when the system will deliver maximum work, when the system is reversible. That means this is reversible work. Reversible work output. So useful work, that means you have to write like that. Second law efficiency, useful work divided by work reversible. You can write also this is work actual obtained by the work maximum. You can write like that. And this is given 0.85. Yes or not? This is given. And mind it, beta, this is the work output device. And if there is a work input device, so just reverse it. So if there is a work input device like a compressor, if this is a compressor, so what is the second law of efficiency? Maximum possible reversible work input divided by useful work input. This is a work output device, so we have to write the second law of efficiency, useful work output divided by maximum work output. Clear? Now, so what is the actual work? That means work actual is equal to 0.85 work maximum. Clear? This is one relation. Now, how to find actual, how to find maximum? Please tell me, beta, how to find the maximum? How to find the maximum? So, if you put the value, we have to find the actual work. So, this maximum work, that means a reversible work. How to find? We have to find, that means this is what? This is your exergy, that means maximum work obtainable. That is your exergy. That means if you find W max, so for that one we have to find the exergy that means maximum work potential, maximum work potential of the air at the inlet conditions. That means we have to find the maximum at according to the inlet condition, that is change in availability of air between state point 1 to state point 2. That means change in availability you have to find, that is your maximum work potential, या exergy या maximum work. So this is your with respect to psi 1, and that is your exergy 1 minus exergy 2. And if you find this one, this is nothing H1 with respect to so that means inlet minus surrounding is dead system up to H0 minus T0 S1 minus S0, okay, plus change in kinetic energy delta Ke plus change in potential energy. Now if the system is stationary, there is no any information of kinetic energy and there is no any information of potential energy, so we have to neglect it. Now sigma 1, why this is 1? Why? Because we have to find with respect to inlet condition, okay. So 1, what is the enthalpy? So this is your enthalpy at point 1. So at point 1, what is the enthalpy is there? At point 1, 1 it is your inlet, that means inter 1600 is inlet, 1600. So at the 1600, what is the enthalpy? 1046. So this is your 1046 minus, this is your exit enthalpy, and the exit enthalpy, it is your 1600, 1000, and 1000 is, oh, this is 1600, na? This is not like that. H1 it is your 1600. So according to 1600, this is how much? 1757. 1757, and this is your exit enthalpy. And what is the exit enthalpy? And exit enthalpy, it is at, you can better to write here H2, no problem. H2, better to write here H2. Clear? No problem at all, okay. So H2, and H2 it is your exit 1000. So at 1000, how much it is? 1046 minus, this is surrounding temperature. How much the surrounding temperature? 298. So there is 298. What is the entropy at 1600? 1600 entropy 8.1349. 8.1349. And what is the entropy at exit condition? 8.6905. 8.6905. 8.6905. 8.6905. We'll check, match this one, no problem. 8.6905, 8.13. Okay. So if you solve this one, this is your 876.57 kilojoule per kg. Clear? Now, my dear, what is this? This is the maximum work potential. This is your maximum work potential. Now, so if you write something here, why? Because this is very important to understand for that one. This is very important. Write some comment. What is that? Please write down. Please write down some comment here. What is that? Every per kg, that means every per kg, every per kg, that means at for 1 kg of air entering the turbine has a work potential of 6.57 kilojoule. Clear? That much of a work potential, that much of a maximum work you have to find for 1 kg of the expansion of the air. That means if you expand 1 kg of air, the turbine is able to deliver that the maximum work, it is for 876.57 kilojoule. Clear? Now, so what is the actual work then? So what is the actual work? Put here 0.85 into what is the maximum? Maximum 876.57. 876.57. Multiply with this one. This is your 745.0845 kilojoule per kg. So this is your actual work. This is your actual work. So we have an actual work, we have a maximum work. If you differentiate with this one, what is the value, beta? If you differentiate this one, what is this value? That is your, what is the value? Exergy destruction. That means irreversibility. That means that much of work, that much of energy is wastage. You can never overcome. That means so what is your maximum? Yeah, this is your W reversible out. What is that? This value? Maximum is what, beta? Please tell me. What is the value maximum? Please tell me. What is the maximum? Yes. The maximum, it is your 876.57 kilojoule per kg. This is your maximum, right? And what is your useful work? Useful, yeah, actual. How much it is? This is your actual is how much? 745.0845 kilojoule per kg. Now, if you differentiate with these two, that means if you differentiate between these two, that means if you differentiate these two, minus, 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 that means work maximum minus work useful or work reversible out minus work actual. This is your how much? 131.49 kilojoule per kg. This is what? This is what, beta? This is what? Please tell me. That means this is your exergy destroyed. Exergy destroyed, or that is called irreversibility. That is called irreversibility. That means the potential to produce useful work is wastage. That means, what is the mean by this one? The potential of produce useful work, the potential to produce produce useful work of, that means this may be useful, but we can never overcome. Why? Because there is a destroyed irreversibility of 131.49 kilojoule per kg of air. That means this, the potential to produce, that means this is the potential to produce, that it is not obtainable. This can be obtained, but it is not obtained, that is your wastage. That means the exergy destroyed could also be determined by calculating the S generation during the process. That means this is a potential to produce useful work. Potential to produce, this is the potential to produce useful work. That means you can reduce maximum to increase the, to produce the maximum obtainable work. So this is your destroyed irreversibility. Okay. Now, so this is your irreversibility. So I think first question it is there. What is the first question is that? So, what is the irreversibility during the expansion? So the second of question, the second is clear. So that is your irreversibility. That is your answer. 131.49 kilojoule per kg. This is your B answer. Okay, this is your B answer. Now the first and the second, first one is, what is the turbine inlet pressure? That means we have to find the turbine inlet pressure. So for this is expansion of ideal gas, and we know that the entropy change, and we know that the entropy change, that means delta S is what for ideal gas? We know that Cp ln T2 by T1 minus R of ln P2 by P1. Clear now? Put all these values. Cp of the air, we know that 1.005, ln T2 we have 1000, T1 we have 16, R 0.287, ln P2 is the final, that means atmosphere 1 bar, but P1 we don't have. Now what is that? And we don't have this one. So one equation, one unknown, we can never form. Two unknown, delta S1 is, delta S we don't have, and P1 is altered. So what is the next step? Very important. We know that what do we know that? Irreversibility is equal to T naught into S generation. We know that this formula. If you don't know, you cannot solve this problem. Okay. And if you take S generation, this is the S generation. This is S generation, and this S generation, if you find this one, entropy generation is equal to irreversibility divided by temperature. This is the temperature of the surrounding. So what is the irreversibility then? Here irreversibility is 131.49, and surrounding, what is the surrounding? Surrounding is how much, beta? 298. 298. If you solve this one, this is your 0.4412 kilojoule per Kelvin. Okay. What is this one? S generation, this is your S total, that means this is your delta S. So if you have a delta S, put this value here. So this is put back here, in this one, put back here 0.4412 and solve this one. The pressure P1, this pressure P1, if you solve, this pressure P1 is 24.12. 24.12 bar. That's it. Clear? This is clear? So from this one you can easily find. So my dear, I will touch the question, the motive of this class today's, I will end up here, no problem. Now the motive of today's class is that in YouTube platform, anywhere you have to see the many platform, I will say I already seen that, but in that platform you are never feel this type of question, you have never seen this type of question, okay? Never see this type of question. Why? Because this question is very important question. This question is our very important question, and not for the gate perspective point of view. This is for the concept, thermodynamic concept point of view. That is the question is very important. Okay. So for my analysis during this situations, all the channel, all the platform have a different questions levels. But in this one there is a very challenging questions, and also we have to also there is a many concept is there. In one concept there is a many concept. So that is the motive of this series of that challenging question. It is not like that if you are how many the question we will cover, but the question how much the question, how many the question we will cover, that question is really very conceptual question. So you have to understand very good. Okay. So I humbly request that this domain, that means the domain of exergy balance, or how to find the exergy, if there is a work is there, if there is a mass is there, if there is a heat is there. So how to find that exergy balance and all the things, irreversibility, entropy, generation, will touch all the things. Okay. So please, I damn sure in this today's 1 and 15-minute classes, 2 marks question is damn sure. Okay, beta. Thank you. Bye-bye. Take care.